This is the second section on chapter 1 on number theory, and this is on the Euclidean algorithm. So before we get started, just some terms that we're going to be using. Now, we all know what the highest common factor is. Highest common factor from GCSE, and we may have found the highest common factor by using factor trees and then Venn diagram. Well, at A level, we now refer to this as the greatest common divisor. It's basically the same thing, but we're going to call it the greatest common divisor, or GCD. And we're going to be using this algorithm to help us find this greatest common divisor. So we're going to be using this Euclidean algorithm to find it. Now, if you've not done D1 or you're not doing computer science, you may not know what an algorithm is. Well, an algorithm is just a list of processes or steps that we carry out. Now, you quite often find you may not understand how those steps work or why they work, but you just follow out the steps, and if you follow those steps exactly, you'll get an answer at the end. So the notation that we use, if I were to write this GCD and then in brackets AB, this means the greatest common divisor of A and B, common divisor of A and B. Now, if, for example, C is just a common divisor of A and B, so a common divisor of A and B, and let's say that D is the greatest common divisor of A and B, then it will always be the case that D will be greater than or equal to C. So in other words, the greatest common divisor, or you can think of it like the highest common factor, will be greater than all the other divisors, all the other factors. So for example, if we had, let's list all the factors of 15 and 20. Well, they do have common divisors, so 1, 3, 5, 15, and for 20, 1, 2, 4, 5, 10, 20. Yeah, they do have a common divisor, 1, but the highest common divisor, or the greatest common divisor, will be 5. So if we call this D, then it's greater than this common divisor here, C. In some cases, the greatest common divisor is equal to the common divisor, because there may only be one common divisor between two numbers. One other fact here is that if, for example, the greatest common divisor of two numbers is equal to 1, we say that those two numbers are co-prime. In other words, these numbers only share 1 as a common factor or divisor. So for example, you might have the numbers 17 and 25. These two numbers only share 1 as a common divisor. So these two numbers, 17 and 25, this is one example. These two numbers are co-prime. Now we've gone through all of that, what we're going to do now is actually get into the algorithm to find the greatest common divisor. So just clear this. So yeah, let's go through this algorithm, Euclidean algorithm, to find the greatest common divisor of two numbers. An example I'm going to use is to find the greatest common divisor of these two numbers, 678 and 262. Now this algorithm all stems from the division algorithm, and the division algorithm says that you have a number which can be written as another number times the quotient plus r, and if we rearrange that, the remainder is equal to a minus bq. So remember, this is when you're doing a divided by b. So this is the dividend, this is the divisor, q is the quotient, r is the remainder. So we can write a division as the divisor times by the quotient plus the remainder, and if you just rearrange this, you get the remainder is equal to the dividend, the number you're dividing by, divided by the divisor. Sorry, that's the number you're dividing by times the quotient. So that's what we're going to use to help us with this. So the first thing we're going to do is we're going to write 678 equal to, so you always start with a larger number there, 678, even if the larger number is written here. Yeah, so always write the larger number is equal to a multiple of the smaller number plus a remainder. So we need to work out 262 times by what plus what remainder gives us 678. Now I've worked this out already. It's 262 times 2, and that will give you a remainder of 154. So that's step number 1. Now with algorithms, there's a set of steps you do, and you just repeat those steps. Now what we do, we repeat those steps now with these two numbers, 262 and 154. So this is what the second line looks like. We are now going to write 262 as 154 times by something plus a remainder. So can you see that the 262 basically gets shifted across to there, the 154 gets shifted across to there. Now if we do that, I've worked this out already, it's 154 times by 1 plus a remainder of 108. Right, now we do the same thing again. The numbers get shifted across. So now 154 gets shifted across to here. 154 is equal to 108 times by something plus a remainder. So can you see at each step what happens is the number in this position gets shifted across to here, and the number in the end position, the remainder, gets shifted across to there. So it's always going to be those steps. Once you've done one step, then the rest is straightforward. So 108 times by 1 with a remainder of 46, I think. There we go. Right, now the rest I'll just do in black now that you can see what we're doing. So 108 over here is equal now to 46 times by something plus a remainder, and it's actually 46 times by 2 with a remainder of 16. So you'll be using your calculator to help you work these out. The 46 shifts across to here, so it's going to be 46 equals 16 times by, in this case it's 2, that'll be 32. That gives you a remainder of 14. The 16 shifts across to here, that's 14 times by 1 with a remainder of 2. Then the 14 shifts across, the 2 shifts here. Now this happens to be 2 times 7 with no remainder. Now when you get no remainder, you stop. So you stop this algorithm, you stop these steps, stop when remainder equals 0. That's when you stop your algorithm. Now, where do you find the greatest common divisor of these numbers? Well, you go to the previous line and you look at the remainder from the previous line. That remainder there gives you the greatest common divisor. So we'll just write that down. Okay, so GCD is the last remainder, because the remainder we got after that was 0. Yeah, so the last remainder here gives you the greatest common divisor. Right, now we can apply this algorithm actually backwards to solve another problem. And this problem is this: can I write the greatest common divisor of a number equal to some multiple of the first number plus another multiple of the second number? And the answer is yes, you can. And we use something called Bezout's identity. And Bezout's identity is using this backwards. Yeah, so actually for any greatest common divisor of two numbers, we can write it as something times the first number plus something times the second number. So for example, in our example, can we write 2, that's the greatest common divisor, as 678, that was the first number, times something, plus 262 times something? And we can. That's what Bezout's identity says we can do. Now, obviously, either x or y is going to be negative, because these are going to be integers, because we've got a number smaller than both of them. So x and y are going to be integers, and I'm going to show you how we do that. So the first step is that we would need to find the greatest common divisor of A and B using the Euclidean algorithm. And we've already done that, so that's not a problem. But you would need to do that first, because we're going to use this algorithm and actually work backwards through it. Once we've done that, the first thing that we do is we're going to use this step here as our starting block. This is where we got the greatest common divisor from, and we're going to rewrite this. This is like this, isn't it? A equals BQ plus R. So I can rearrange it and write R, or 2, is equal to A, which is 16, minus BQ, 14 times 1. So the first step is to rearrange the GCD line. Now what I mean by the GCD line, that's the line of the working that gave us the greatest common divisor, so I'll call it that. Rearrange the GCD line so that we have R equals something, and we're going to use back substitution. Now this will all make sense as we work backwards, so let's go through it. So step number 1, 2 is equal to 16 minus 14 times 1. So that's my first step. Yeah, all I've done is rearrange this. Now whenever I get these multiplications here, we're not going to multiply them out, we're going to leave them like this. You're going to see what's happening. Right, so I'm going to put a tick by this step here because I've used it. Now I'm going to go back to the previous step here. Now if I use this, I can write 14 equals 46 minus 16 times 2. Now I've actually got a 14 here. So this 14 here can be rewritten as 46 minus 16 times 2, because that was from the previous step, and that's what we're going to do. So next step, 2 equals, let's get the right colour, 2 equals 16 minus, now it's not 14 times 1 now, it's going to be 46 minus 16 times 2 times 1. Yeah, so I've replaced that 14 with this, and I've got that from the previous line. Now, before we move on, what we're going to do is we're just going to group together the like terms. So I've got a 16 here, and I've got a 16 here. We're going to put them together. Right, so if we basically expand the brackets and simplify that, it will become 16 times 3 minus 46. Okay, 16 times 3 because I've got 1 times 16 here, and then the minus makes 2 times 16. So altogether, when expanded and simplified, I get 3 times 16. Right, now the next line is going to be, well, let's tick the line that we used. So we've just used that one. Yeah, so now we've got 16, and we're going to use this line to write 16 as 108 minus 46 times 2. So I'll take this 16 here, and using the previous line of working, I'll write it as 2 equals, not 16 times 3, but now 108 minus 46 times 2, that's where 16 was, that times by 3 minus 46. So the 16 has been replaced with this, and that came from the previous line. Again, we'll group together terms and tidy this up. So this will become 2 equals 3 times 108, from expanding the brackets, minus 7 times by 46. Yeah, because we've got negative 2 times 46, or 2 times by 46, times that by 3, that's going to be negative 6 lots of 46. Take away another 46 is going to be negative 7 lots of 46. Right, and then we carry on. So the next step now is going to be replacing the 46 here. And where do we go to find what we replace 46 with? This line here. So the next line is going to look like this. 2 equals 3 times 108 minus 7 times by, now 46 we'll replace with 154 minus 108 times 1. So we just keep this back substitution. 46 replaced with that minus that. Let's simplify that. So that will give us 2 equals 10 times 108 minus 7 times 154. And we go back a step. So we've used, we're now going to this one, we're going to replace the 108. So the 108 that's here will get substituted. And if we do that, that will give us 2 equals 10 times by what we substitute for 108, which is going to be 262 minus 154 times 1 minus 7 times 154. Just like before, we simplify it, we group together the terms. That will give us 10 times 262 minus 17 times 154. Then we're up to the last line here, and what do we substitute? The 154. Notice that it's the remainders that we change. Yeah, every time you see a remainder, you look at the previous line and it will tell you what to change. So all of these numbers get changed apart from the 2, 14, 16, 46, 108, 154. They get replaced with what's over here. Right, yes, so 154 is going to get substituted. So now if I do that, I'll have 2 equals 10 times 262 minus 17 times by and that substitution is going to be 678. This is the very first line of working, minus 262 times by 2. And then all I need to do now is to say, right, how many lots of 678? Well, if I work that out, that's going to be minus 17. And how many lots of 262? That's going to be 44, I believe. So we've written 678 and 262, multiples of these is equal to the greatest common divisor. So we've solved this problem here, and what we've got is x equals negative 17, y equals 44, and you can use your calculator to check that that answer actually does work. So if we do 678 times by negative 17 plus 262 times by 44, we do indeed get 2. So this is the method that we use to write the greatest common divisor of two numbers as multiples of those two numbers, and we work out what the multiples are. Okay, so we've got 3 questions here where we're asked to find the greatest common divisor. Now we're not actually using the algorithm for these, we are just doing it by eye because we don't need an algorithm. We can see clearly, I can see the greatest common divisor of 3 and 12 is just 3. Yeah, if I were to list the factors of 3 and factors of 12, I can see that the greatest common divisor is 3. Okay, B, greatest common divisor of 25 and 25. Well, that's just the number itself, 25. So again, if I listed the, I shouldn't say factors, divisors of 25, 1, 5, 25 for both numbers, then yeah, again, greatest common divisor is just 25. And then the last example, greatest common divisor of 90 and 84. Now I'll probably do this by listing factors, I think. Actually, I won't list our factors, there are too many, so I'm going to use factor trees like this. And a factor tree for 84. So that would be 6 and 7, and then 2 and 3. Let's put these in a Venn diagram. So this is not the method we're really using, just doing it for this question here. And what do I have in both factor trees? A 2 and a 2, so I can put a 2 in the middle. What else? There's a 3 and a 3, so I'll put a 3 in the middle there. I don't need to do the rest of the factor tree because I only want the greatest common divisor, which I'll get by multiplying those. So that's going to be 2 times 3, so that's going to be 6 as the greatest common divisor of 90 and 84. Right, use the Euclidean algorithm to find the greatest common divisor of 306 and 657. So we want to find this 306, 657. Now remember, we start with the larger number first, so we write 657 equal to 306 times by something plus a remainder. So 306 times by 2 is 612, so that goes into it twice. So I can then work out the remainder. So if I subtract 2 times 306 from 657, which is 612, that leaves a remainder of 45. Now remember, with this algorithm, these two numbers, we shift across and we do the same thing again. So now we have 306 equals 45 times by something plus remainder. Now 45, let's see, 45 times 6, yeah, 45 times by 6, which is 270 actually. Can I get 7 lots? No, to 6 lots. So 45 times by 6 is 270 times by 6. So if it's 270, that leaves a remainder of 36. So these two numbers get shifted across. We do the same thing again. So 45 equals 36. Well, that's just going to be times by 1. And that's going to leave a remainder of 9. We shift these two across, do the algorithm again. So 36 equals 9 times 4 with no remainder. So remember, when there is no remainder, you stop the algorithm and you find the greatest common divisor here. So we can write down the greatest common divisor of 306 and just comma 657 is 9. Okay, so this question says to use Euclidean algorithm to find integers x and y such that the multiples of these numbers is equal to the greatest common divisor. Now we've already done that in a previous example, so I've just pasted my working in here because we're going to be using this to find the values of x and y. So remember, we start at the line of the working where we've got our greatest common divisor, and we're going to write 9 equals 45 minus 36 times 1. So 9 equals 45 minus 36 times 1. Then you look at your previous line of working. 36 equals 306 minus 45 times by 6. So the 36 I will replace with 306 minus 45 times 6. So this is basically like 36 times by 1. Now before we move on, remember to group together any terms. So we've got a 45 here, and then a minus and minus. This is like plus 6 times 45. So in effect, we've got 7 times 35. So, sorry, 7 lots of 45. 7 times by 45 minus 306. Right, okay, so we've used this line of working here. So now we go back to this line of working and we can write 45. So the 45 that's here, we can write that as 657 minus 306 times 2. So 9 equals 7 times by, so replace the 45 with 657 minus 306 times 2, and then that's minus 306. So the last line is basically to group all of these together. So what have we got? We've got 7 lots of 657. So let's write that as 657 times 7, because I just want to write it like this sort of format. And then here this is going to be negative 2 lots of 306 times by 7 is going to be negative 14 lots of 306. Take away another 306 is going to be negative 15 lots of 306. So 306 times by, I've forgotten what that number was now. Oh, negative 15, wasn't it? Times by negative 15. So whenever we we do this, it's useful to check on your calculator that actually this works. So we'll do that. 657 times by 7 plus 306 times by negative 15, and that gives us 9. So it does work. So I'll just finish it off writing it exactly the way they've got it. 306 times by negative 15 plus 657 times by 7. So x equals negative 15 and y equals 7. Okay, use the Euclidean algorithm to find integers x and y such that the greatest common divisor of those two numbers is equal to multiples of those numbers. So the first thing that we're going to do is actually to find the greatest common divisor of these two numbers, 1, 4, 3 and 2, 5, 2. So we use the Euclidean algorithm to do that. So we'll write 252, remember the larger number, equals a multiple of the smaller number. Now if I double that, it's going to be 280 something, so it's only going to be one lot of that plus a remainder. So if I do 252 and take away 143, I get a remainder of 109. So remember, these two numbers shift across. We do the same thing again. So 143 equals 109 times something, well that's only going to be 1, plus a remainder, and 143 minus 109 is 34. So again, shift across these two numbers. 109 equals 34 times by, right now I reckon it's 34 times 3, that's 102, yeah. So if that makes 102, that leaves a remainder of 7. Shift across these two. So now we have 34 equals 7 times by, now 7 times 5 will be too big, that'll be 35, so it's going to be 7 times 4, which is 28, with a remainder of 6. Shift across these two, and then we'll have 7 equals 6, well, it's only going to be times by 1 with a remainder of 1, and shift those across. Let's put them in the right colours. So then that will leave 6 equals, well, it's just 1 times 6 with no remainder. So that means that the greatest common divisor of those two numbers is 1. They're co-prime. The GCD of 143 and 252 equals 1. Therefore, they are what we call co-prime. The only common factor or common divisor that they share is 1. So now we use the algorithm here in reverse to find these values of x and y. So remember, we start with the line where of working where we got the GCD from, which is that. So we will rewrite it as 1 equals 7 minus 6 times 1, like this. We go to the previous line. 6 can be written, so 1 minus, or 1 equals 7 minus, instead of 6, I write 34 minus 7 times 4, and that's going to be times by 1. We simplify it before moving on, so that would give us, what have we got here, a 7, and then this will be adding 4 lots of 7, so that'll be 5 lots of 7. So that'll be 1 equals 5 times 7, and then minus 34, which makes sense. 35 minus 34 is 1. Then the next line of working, what I'm going to do is go back to here. So now replace the 7. So 5 times by So the 7 gets replaced with 109 minus 34 times by 3 minus 34. Again, we tidy that up. So we've got 5 lots of 109. Then we have, now that's going to be negative 3 lots. So we've got negative 15 lots when we expand the brackets of 34. Negative 15 lots of 34. Take away another 34, so that's negative 16 lots of 34. So the next line of working, go back to here, I'll replace the 34. So I'll have 5 times 109 minus 16 lots of 34, but I replace 34 with 143 minus 109 times 1. So again, we simplify it before moving on. So I've got 5 lots of 109. When I expand the brackets, I will have plus 16 lots of 109. So 5 plus 16 is 21. So I'll have 21 lots of 109. Then I'll just have negative 16 lots of 143. So minus 16 times 143. Then we move back to this here and we replace the 109 in our working. So 1 equals, so 21 times the 109 we replace with 252 minus 143 times 1 minus 16 times 143. And what we do from here is again group together like the like terms. So I've got 21 lots of 252. So that's dealt with. Now I have negative 21 lots of 143 minus 16 lots. So that will give me negative minus 37 lots of 143. So now we've got it in the form that's required. So x is the number of 143s. So x equals negative 37 and y is the number of 252s. So y equals 21. So here we have to find the greatest common divisor first before then using the algorithm in reverse to find the values of x and y in this Bezout's identity here. Okay, so use the Euclidean algorithm to show that 49 and 60 are relatively prime. So relatively prime is another way of saying coprime. So you can say coprime or relatively prime. It basically means that their greatest common divisor is 1. Right, so first thing is to write 60 equal to 49 times by something plus a remainder. Well, it's going to be times by 1 with a remainder of 11. Shift across the 49 and 11. So you've got 49 equals 11 times something, which is 4. So that's 44 plus a remainder of 5. Shift across the 11 and the 5. So 11 equals 5 times, well, it's going to be 2 plus a remainder of 1. Shift across the 5 and the 1. 5 equals 1 times by 5. No remainder. So we stop. We look to the previous line here. The remainder there will tell us the greatest common divisor. So the GCD of 49 and 60 equals 1. Therefore, 49 and 60 are relatively prime or coprime. Means the same thing. Right, part B. Find integers x and y such that the multiples of x and y equal 1, right? So this is where we start with this part of our working, work backwards. So 1 is equal to 11 minus 5 times 2. I suppose I should put part B here, like this. Going back to the previous line, we're going to replace the 5. So look at the remainder. So the 5 will replace with, let's write it as minus 2 times by the 5 that we're going to replace, which is going to be 49 minus 11 times 4, like this. So remember, group together the terms before you move on. So I will have one lot of 11 here. When I multiply this bracket, I will have plus 8 lots of 11. So that gives me 9 lots of 11 minus 2 lots of 49. Then we move to the first line of working. So I replace the 11 here. So 9 times by 60 minus 49 times 1 minus 2 times 49. We can group together the terms. So we'll have 9 times by 60. Then I will have minus 9 lots of 49 minus 2 lots of 49, which gives me minus 11 lots of 49. So 11 lots of 49. So these are the numbers I'm looking for. Now the number of 49s I've got, x is negative 11, and the number of 60s I've got, y is 9. Now part C says, hence find the integers p and q such that 49p plus 60q equals 5. Now the only way this would equal 5 is if they had a common factor of 5. This remainder is 5, and that's not going to happen. So we're not going to be able to use this process here, the Euclidean algorithm, and then work backwards to find a number 5, because they haven't got a factor of 5. So the only way to answer that question is actually to take the original identity we've got and times it by 5. So I had 49 times by negative 11. So this is what I worked out from before. Plus 60 times by 9 equals 1. Now if I'm going to get this to equal 5, well, I'm just going to have to times everything by 5. That's the only way that's going to happen, because 5 is not a factor of these two numbers. It's not a divisor of these two numbers. So if I just times everything by 5, basically I want to times these multiples here by 5. So that will give me this, 49 times by negative 55 plus 60 times by 45. That will equal 5. And we can check that on our calculator. And that works, that checks out. So P is equal to negative 55 and Q is equal to, my multiplication is not right. 9 times 5 is 45, not 49. Q equals 45. So you should now be able to do exercise 1b on pages 9 to 10. Now in terms of a recap, I'm not going to go through the whole algorithms again, because you can look at the first slide for those, but we've got this Euclidean algorithm that allows us to find the greatest common divisor of two numbers. We have Bezout's identity, which tells us that the greatest common divisor of A and B can be written as some multiple of the two numbers which we found the divisor of. If the greatest common divisor of two numbers is 1, then we say the numbers are co-prime, or you could use relatively prime. Both mean the same thing. And the greatest common divisor of two numbers is always greater than or equal to a common divisor of two numbers.